Alright, so I'm thinking about two more of these will do the trick. The last thing I was talking about was the electroscope. Let's say it has negative charge. What happens if a positive object is brought near? The negative charge is stored throughout this electroscope. That means the leaves are negatively charged. We bring a positive object near this metal knob, it's going to draw electrons from the entire object up towards the metal knob. If the electrons get drawn out of the leaves, which are right now separated because both of them are negative and like charges repel, then if there's less negatives there, then the leaves will not repel as strongly and they will collapse back inwards. So, what happens if we put a positive object near the top of a negatively charged electroscope? Well, then the leaves must collapse. They go back towards each other. They come back together a little bit. Not all the way, but a little bit. If you were to remove that positive object, the leaves would spring back out. Okay? If you were to tap the positive object on the metal knob, then the leaves would probably, depends on how much charge there is, but the leaves would move together again because now you've taken some of those negatives off. Now there's not going to be as many negatives to repel each other down here. The leaves will collapse back inwards. What if the object is negative? Okay? What if the object being brought near the electroscope is negative? Well, you have negative charges throughout the electroscope. You bring a negative object here closer to it, the negatives are going to repel. The negatives in the electroscope are going to repel away from the negative object. They will go towards the leaves. The leaves will have more negatives in them. They will spread out even more. Okay? The leaves will spread even more. And again, if I don't think I can really show this well with a video. There are plenty of videos online where someone actually filmed what this happening. If you want, I have plenty of electroscopes back here. You can come and you can test them out for yourself. Okay? That's all I want to say about electroscopes. Not a huge part of this course, but you should know the function of them and you should know how they work. Alright, the last bit of electrostatics that we will practice is electrostatic force. Like I said, no electric field, no electric potential except for circuits. We're not going to do electric potential of like isolated charges, thankfully. Electrostatic force. Okay, let's scroll down a little bit. Now, what this is, okay, it is just simply the force. It is the force between two electric charges. It's the force between two electric charges. And the value of this force, or the equation for this force, should look kind of familiar to you, definitely from last year, but also just in general. K, Q1, Q2 over R squared. Okay? This is going to be reflected in the gravitation equation later on in our last unit. Now let's define this. This is obviously electrostatic force. K is not spring constant. Okay, I have people telling me K is spring constant here. No, this has nothing to do with springs. K is the electrostatic constant. And it has a value. Last year I believe it was 8.99 times 10 to the 9th. Newtons times meters squared over Coulomb squared. That's what we use. Even simpler this year. It is 9 times 10 to the 9th. Newtons times meters squared over Coulomb squared. The units are important. In the reference tables, they also list this as the electrostatic constant. They list it as 1 over 4 pi, and then kind of like a slanty E with a 0 next to it. This is known as an epsilon naught. Okay? This is just something you see on the equation sheet. It has importance in physics, but I don't think it has importance to you guys. So if you ever see this, don't get freaked out, okay? They're just trying to make you look at the equation sheet. They're making sure that you know that epsilon naught, it's a constant with its own value, and it kind of helps us determine this number, okay? I don't really want to get into why that number is the way it is. Anyways, it's something that you should be aware of if you ever see it in a question. It's not something you have to be super familiar with. Okay, so that's the electrostatic constant. Q1 and Q2 are the two charges in question. And then R is the distance between the centers of charge. So if you have two charged objects, r is the distance between their centers, the centers of those charges. Real quick example before we get into our actual tutorial. We have a hydrogen atom, let's say, where the electron and the proton are 5.2 times 10 to the negative 11th meters away from each other. We want to determine two different things, the electrostatic force and the gravitational force between the two particles. Let's do this side for electrostatic, and this side for gravitational. The electrostatic force is given up there. It is equal to Fe equals K Q1 Q2 over R squared. We know that K is 9 times 10 to the 9th newtons times meters squared over coulomb squared. Q1 and Q2, wait a sec, what the heck are Q1 and Q2? Well, let's see, my two charges in a hydrogen atom are electron and proton. And I know, since I'm dealing with, I got coulombs in the units here, so I need their charges in coulombs. So the thing with this equation is you have to put in the magnitude of the charge. Don't try and put negatives in here. Like, don't say, oh, electron's negative, so I gotta put negative. No, don't do that. We just want the magnitude of the charge. If you remember from before, the charge, the elementary charge value is 1.6 times 10 to the negative 19th coulombs. And that is the same for an electron and a proton, which is kind of interesting because if you remember anything about chemistry, electrons are tiny, protons are much, much bigger than an electron in mass, yet they have the same charge. Very interesting. They are separated by 5.2 times 10 to the negative 11th meters. Don't forget to square that. You should verify this for yourself. Make sure you can still type numbers into a calculator, but if you multiply this out, it becomes about 8.52 times 10 to the negative 8th newtons, a very small force. Let's talk about the gravitational force between these. Sometimes people used to think that gravity holds atoms together. You could not be more wrong. Okay, that for Regents kids should be familiar from last year, the gravitation equation. Big G, m1, m2 over r squared. Notice it has a very similar form to this one. So let's figure out what this is. Big G, and here's a picture of the reference tables. Let me show you where all this information is located. Let's see. Electron charge magnitude, right here. E equals 1.6 times 10 to the negative 19th C. Okay, same for both electron and proton. Big G, 6.67 times 10 to the negative 11th. Oh, they got weird units for that. Newtons times meters squared over kilograms squared for big G. It says M1 and M2. I need the masses of the two objects that I'm trying to find the force of gravity between. Oh, look at that. Proton mass, electron mass. Okay? All this information is on the top, on the constants table in the reference, on the reference sheet. So, let's plug in. 6.67 times 10 to the negative 11th newtons times meters squared over kg squared. And of course, I have just forgotten what the heck the mass, okay, so mass of the electron, 9.11 times 10 to the negative 31st kilograms. And, oh yeah, I have a sheet in front of me. Mass of a proton, oh, I'm running out of room, 1.67 times 10 to the negative 27th kilograms. Okay, hopefully you can forgive my bad handwriting. And the distance between them, 5.2 times 10 to the negative 11th meters squared. You do the math here, you multiply all this out, which you should confirm that I am getting the right answer. You get a force of gravity of 3.75 times 10 to the negative 47 newtons. We thought this was small. This is almost 40 orders of magnitude smaller. Oh my god, I cannot write today. Orders of magnitude smaller. That's much smaller. And this is inherently bigger. Very interesting, okay? People think sometimes that gravity holds everything together. That is true on large scales. By large scales, I mean things like the size of asteroids and up, okay? Gravity is strong enough, there's enough mass at those levels, and there's not really any big charge imbalances to hold those objects together. But on an everyday scale, everyday people scale, it is absolutely the electrostatic force that holds things together. Electrostatic force is much more important in holding an atom together than the force of gravity. This, if there ever was something that's negligible, that's negligible. Okay? That is essentially all the basics that you need to know about the electrostatics. That is all you really need. What we're going to do now is just practice in an AP-like setting. I want to get through this quick. I don't want to make you watch any more videos, and maybe one more. Here's our setup. We have 3 point charges, A, B, and C. Point charge is just a charge, it's a small charge. It's spherically symmetric. It can be reduced down to a single geometric point. These point charges have magnitudes of charge. +2 or +2 elementary charges, -7 elementary charges, +8 elementary charges, and they are arranged as shown below. This first one is a student hypothesis question. Okay? Student hypothesis questions are more and more common on the AP exam. The student will say something that's correct, something that's incorrect, maybe multiple correct and incorrect statements. You have to say which is which. The student hypothesizes that if charges A and B are brought together, excess electrons will flow from B to A, giving each a charge of -2.5 eV. Explain in paragraph form what parts of the student's hypothesis, if any, are correct, as well as what parts of the student's hypothesis, if any, are incorrect. Okay? So there's going to be multiple parts of the hypothesis. We need to label them. Student hypothesis that if you do this, if you bring them together, excess electrons will flow from B to A. Let's see if that is correct. We know from before that electrons move from more negative to less negative. It says that B has a charge of -7 elementary charges. A is +2 elementary charges. Is this more negative than this? Is it going to flow from B to A? Absolutely. That will absolutely happen. Okay? This is more negative. This is positive, but you can still think of it as less negative. There's fewer electrons over here. Okay? A lack of electrons. So the electrons will flow from B to A. That is correct. Okay? So we might as well start off by saying the student is correct that excess electrons will flow from B to A. And once you say whether he's correct, you got to explain. Why they're correct. Okay. So we're going to say since B has a negative charge, the extra electrons don't want to stay near the other electrons. The extra electrons want to move away from one another. They don't want to be near each other, okay? Those extra electrons are all tightly packed on B. They do not want to be near each other. They want to get out. They want to go away, okay? So, I guess that should be a comma. So, they move toward the positive charge on A. Okay, you've explained why, you've said what they're right about, and you've explained why they're right. Let's look at the second part of the hypothesis. Giving each, okay, the electrons flow, and each object now has a charge of -2.5 elementary charges. Is this right? No. This is incorrect. So we start off with, however, the student is incorrect about the final charge on A and B. Okay? The student is incorrect with the final charge on A and B. The reason that they are incorrect is because negative 2.5 elementary charges, that is an impossible amount of charge to have in one location. What you're saying is you have half of an elementary charge, half of an electron. That is not how this works, okay? There is no such thing as half an electron. A and B cannot have 2.5 electrons. I guess I should say excess electrons. So, or in excess. Okay? This is because charge is quantized. Charge is quantized, and the smallest amount of charge allowed is plus or minus 1 elementary charge. So, what actually happens here? Can you split this evenly? How did he get negative 2.5 in the first place? Well, he added these two, negative 7 and positive 2. He added them, he got negative 5, and he divided them between A and B. Negative 5 divided by 2 is negative 2.5. It turns out that in this case there is no